Hello everyone. Thanks to everyone for watching this video. My name is Qi Da. I am an architect and engineer. Today's video is titled Continuous Composite Beams, and it is going to provide you a broad overview of the continuous beams and also the resistance in hogging bending. I am going to give you an overview of what I am covering today's video. First of all, we will have a look at some fundamentals of the continuous composite beams, then move on to the plastic and elastic resistance in hogging bending, then wrap up with conclusions. A continuous beam in a building may be interrupted by its supporting internal columns, and both are usually part of a framed structure. Beam-to-column joint is assembly of basic components that enables members to be connected together in such a way that the relevant internal forces and moments can be transferred between them. In this video, I will discuss the continuous composite beams to hogging bending. First, we will introduce the plastic moment of resistance in hogging bending. On effective cross-sections of beams is applicable, except that the effective width of the concrete flange is usually less at an internal support than at midspan. Longitudinal reinforcement will be provided over the whole width of the slab, but only that within the effective width is assumed to contribute to the hogging moment of resistance of the beam. For hogging bending, the effective span LE is the approximate length of the hogging moment region, which can be taken as 1/4 of each span. So, at a support between spans of length L1 and L2, the effective width of a T-beam with pairs of stud connectors at the lateral spacing BL becomes this equation, provided that at least half of B effective is present on each side of the web. A cross-section of a composite beam in hogging bending is shown in Figure A. The steel bottom flange is in compression, and its class is easily found. To classify the web, the distance XA of the plastic neutral axis above G, the center of area of the steel section, must first be found. Let AS be the effective area of longitudinal reinforcement within the effective width B effective of the slab. Welded mesh is normally excluded, because it may not be sufficiently ductile to ensure that it will not fracture before the design ultimate load for the beam is reached. The design tensile force in this reinforcement is this equation, where Fsk is its characteristic yield strength. If there were no tensile reinforcement, the bending resistance would be that of the steel section, as expressed here, where WAPL is the plastic section modulus and FYD is the design yield strength. For rolled sections, it is not necessary to calculate the forces NA in the stress blocks of depth half of HA, nor the lever arm ZA, because values of WAPL are tabulated, but for plate girders, NA and ZA have to be calculated. The simplest way of allowing for the force in the reinforcement is to assume that the stress in a depth XA of web changes from tension to compression, where XA is given by this equation, provided that XA less than or equal to HA/2 minus TF. The depth of web in compression is given by this equation. Knowledge of alpha D/TW and Fy enables the web to be classified, as shown in this figure. The lever arm Z for the two forces Ns in Figure B is given by this equation, where Hs is the height of the reinforcement above the interface. If both the compression flange and the web are in class 1 or 2, this is the appropriate model, and the moment of resistance is this equation. Next, we will introduce the elastic moment of resistance in hogging bending. In the preceding calculation, it was possible to neglect the influence of the method of construction of the beam and the effects of creep, shrinkage, and temperature, because these are reduced by inelastic behavior of the steel and become negligible before the plastic moment of resistance is reached. Where elastic section analysis is used, creep is allowed for in the choice of the modular ratio N equal to EA over EC effective, and so has no influence on the flexural properties of cross-sections with no concrete in compression. In buildings, the effects of shrinkage and the temperature on moments of resistance can usually be neglected, but the method of construction should be allowed for. Here, we assume that at the section considered, the loading causes Hawking bending moments MAED in the steel member alone and MCED in the composite member. The small difference, approximately equal to 3%, between the elastic moduli for reinforcement and the structural steel is usually neglected. The distance xe of the elastic neutral axis of the composite section above that of the steel section is found by taking first moments of area about the later axis, as shown in this expression. The second moment of area of the composite section is this equation. With unpropped construction, the loading at which the steel bottom flange used in compression, at level 4 in Figure A, is usually lower than that at which the slab reinforcement used in tension. The compressive stress due to the moment MAED is this equation. The remaining stress available is Fyd minus sigma 4a, so the yield moment is this equation. The design condition is MCED less than or equal to MCRD. The bending moment MAED causes no stress in the slab reinforcement. In propped construction, for which MAED approximately equal to 0, the tensile stress sigma s in these bars may govern design. It is expressed here and must not exceed FSD. From conclusions what we learned, a continuous beam in a building may be interrupted by its supporting internal columns, and both are usually part of a framed structure. Beam-to-column joint is the assembly of basic components that enables members to be connected together in such a way that the relevant internal forces and moments can be transferred between them. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.